Digital imaging part 3. Digital exposure technique system. So first we have a fixed KVP system, which is where we use the optimum or the highest KVP for the body part. Then we double or half the mass for every 5 centimeters of patient thickness. A variable KVP system is where we adjust 2 KVP per centimeter of subject thickness. Now, the ASRT recommends the first one because it lowers patient dose since it offers the highest KVP with the lowest mass. There are suggested optimal KVP ranges for DR systems, which means we can increase our KVP for imaging body parts with digital systems. For example, the chest should be performed at 110 to 130 kVp. Looking at the chart here, we've got a fixed KVP system that shows the KVPs being 80 kVp, and then for the part thicknesses, we're just going to increase the mass accordingly. For the variable KVP system, we're going to have the mass be the same, which is a high mass, and we're going to use a low KVP and then increase the KVP by 2 for every centimeter of thickness of increase in part thickness. So the first one, fixed KVP system, is going to be recommended by the ASRT to use and be used, and also since the dose is lower. DI numbers, deviation index, indication of variance from established target EI values. So the target range is minus 0.5 to plus 0.5. That would be ideal. Plus 1 to plus 3 would be overexposure, and less than 1 would be underexposure. You wouldn't repeat until you get to less than 3, and over 3 is where we want to look at possible excessive exposure also. Now, of course, this is from the AAPM, so it's a little bit stricter than what many departments use too. So looking at this, we have a deviation index of minus 7.3. So we have extreme underexposure with this one. And so we can see the quantum noise that was on this image. Artifacts. Artifacts are something unwanted. Sources of artifacts, there's many of them. The low contrast and artifacts, imaging plate, the CR reader, digital image processing, operator errors, and finally bad DELs we'll take a look at. So imaging plate artifacts, the appearances are cracks or scratches or tears. It appears plate deteriorates. The cause is rough handling that causes permanent damage to the imaging plate, and the solution is to replace the imaging plate. So for example, we have a imaging plate that has been dropped a lot, and then this is a different imaging plate that was used, but we can see the effect on the image of where light was able to get into the imaging plate. You can see light spots that appear as foreign bodies, and that's from dust or other foreign material on the imaging plate. And that's that the solution would be that CR plates can be cleaned according to manufacturer's recommendations to avoid damage, and also to clean the cassettes so we don't see artifacts. Pathologic conditions. So we've got what appears to be a pathologic condition here, but all it is glue on an imaging plate. So imaging plates, again, can be cleaned. A dark line artifact. The dark line is from, again, imaging plate artifact. It's transmitted to the back of the cassette, and the line corresponds to the cassette hinge where the lead coating was weak or cracked. Solution is to reduce backscatter by collimating, and the exposed imaging plate must be stored safely. In CR, if there's a white line artifact, it means that there's dirt on the light guide in the CR reader, so the light guide must be cleaned by service. The appearance in this one could be like a flag appearance, I guess you could say, or Freddy Krueger sweater. We've got the cause is the plate reader with 2 loaded imaging plates in a single cassette. After the exposure, the bottom imaging plate was extracted, read, and replaced as usual, leaving the top imaging plate to be exposed numerous times. So that double loading the cassettes can be found during cleaning. And if there's 2, then imaging plate should be erased before being put back into use. A ghost image. Incorrect erasure setting was used to eliminate a previous image, or extreme overexposure was performed of the first image. So there might be a need for 2 erasure cycles to completely remove the image. Dark or light image, the cause would be histogram analysis error. Proper collimation, centering, etc. would be different solutions for this one. And so here's our images we took a look at earlier, where we have the histogram analysis error in this one because we only have one border. A black halo surrounding a prosthesis, creating an appearance that the prosthesis is loose. The actual problem is the cause was an edge enhancement artifact, and we don't want to use edge enhancement for diagnostic radiology. Compression artifact is a loss of data, so we call it lossy compression, which is irreversible compression, and we don't want to use that for mammography. There's going to be some loss in image quality. Fog. So image A, which is the first one up here, the background radiation from a plate that wasn't erased for a week, and all it just showed up in the image. And image B is where scatter was on the image due to a plate propped up in a room. So erase cassettes and do not put a CR cassette in a rad room during exposures is the solution. The incorrect receptor exposure for lateral projection of the wrist. So the PA projection was performed correctly, but they used one imaging cassette to perform both images. The technique wasn't changed for the lateral. So one correction could be to correct your exposure, your technique, but number 2 is to take one image per cassette. The appearance is going to be a bunch of white lines, almost like a flag appearance. The cause is a white mesh cart loaded with unexposed imaging plates was placed near a source of scatter, and the solution is to protect imaging plates from sources of scatter and erase anything that does have any type of need to be done so. Grid lines with low contrast, poor grid alignment would be one cause, and align the grid. But you can see the grid lines pretty well on this one. Moray pattern, caused by using a grid with the frequency of 33 lines per centimeter or less that was oriented with the grid lines parallel to the plate's reader scan lines. So you don't want to use grids with anything less than 60 lines per centimeter. And grid lines should run perpendicular to the plate reader's laser scan lines. Imaging plate exposed through the back of the cassette. So you want to make sure that you position the imaging plate correctly. We don't want to put it upside down. There's lead in the back of that cassette. Flat panel detector artifact. So we have a white line. This is from a flat panel detector, bad column of Dells, and we'll do the dead pixel correction we talked about earlier. So now let's move on to informatics. So let's talk about PACS, Picture Archiving and Communication System. So BMI stands for Biomedical Informatics. This is BMI. It's a network group of computer servers and archives to manage digital images, and the key is images that are configured in a manner. It facilitates storing, retrieving, and distributing medical images. It improves efficiency, and it's regulated by the FDA and HIPAA. So it's all about images. We're talking about organizing images after acquisition, post-processing images, designating image storage, backup archive of images. We're looking at retrieving stored images and displaying them, and also distributing or communicating content of images to reviewers. So here's our picture of our different systems. This is the HIS, the HIS, the hospital mainframe computer, and the RIS. And then there's the PACS system over here, which is important to us because it's going to store our images. Here's a satellite image, radiologist home, which is a castle, of course. And we've got all of our different modalities at the top. HIS and RIS are also BMI platforms. HIS is a hospital information system, which involves patient information, text information. It's going to be billing, accounting, and interaction with other departments. RIS is all about radiology, so it's a radiology information system. It's patient registration and tracking, exam scheduling, and diagnostic reports. The RIS PACS broker, the PACS is concerned with image data. The RIS is concerned with textual data. So they both are radiology, but one is for text information, one is for image. The broker acts as a translator for the two of them so that they can communicate. And the web server allows users to access images remotely using internet browser technology and microcomputers. In the top system, we have the broker. So the broker is that translator between the RIS and the PACS, between these two. In the bottom image, we have no broker. We just have two separate systems here. So it's a brokerless technology. EMR and EHR are electronic versions of a patient's collection of medical documents. So in the past, it was all War and Peace on paper. Now it's electronic. So EMR stands for electronic medical record, or EHR, electronic health record. So it's a secure, real-time, point-of-care, patient-centric information resource for physicians. It's improved data integrity and quality of care, as well as increased productivity from satisfied healthcare providers. And so we have medical legal records. DICOM was implemented as a standard in 1993 and has become the most widely used healthcare imaging standard across the world. And so it's going to be universal standardized format and protocol that addresses the standard for communication of images. HIPAA is a federal law that requires that all communications concerning healthcare information have features to safeguard identity and confidentiality of information being communicated. Requires the information to be encrypted and have all patient identifiers removed and be scrubbed of all except for relevant data fields. The HL7 addresses communication of textual data between the RIS and the HIS. And so what it basically does is it handles textual data exchange. So the IHE promotes the use of DICOM and HL7 as well as standards. So DICOM handles mainly image data. HL7 handles textual data exchange. The information systems are the PACS, the HIS, the RIS, the voice recognition system used by radiologists, and electronic teaching and research file systems that are housed within PACS. Network. The network allows computers to exchange data and share resources. It's kind of like a traffic light between data destinations. The bandwidth describes how much data can be moved and is measured in bits per second. The LAN, which is a local area network, connects all the computers in a system and often uses a special wiring system such as an Ethernet. LANs can be linked with bridges. They have a bandwidth of 10 megabits per second. An example is an intranet. The examples of LANs are the bus network shown on the left-hand side, the star network in the center, and the ring network on the right. And that's where all the computers are together, are networked together. WAN stands for Wide Area Network, and that's where information leaves the system to go to a remote location. And that's teleradiology. It operates at a slower speed, and the example is the internet. The PACS is the main computer, and that's the heart of the system. Consists of a high-end computer or server, often called a PACS controller, database server, or image server. It's well equipped with several CPUs that can process data very quickly, a substantial RAM and cache memory. The length of storage. Many institutions store images for 5 to 7 years. Pediatric and litigation films are retained indefinitely. The exact number is determined by state laws. PACS eliminates the need for most of the storage space and requires immense amounts of memory and is based upon a 3 to 5 year storage requirement. 10 to 16 terabytes would be required for a complete digital PACS system. Types of storage. Short-term, local modality hard drive, disks, tapes, and optical disc. Upon completion of the exam, the PACS server and RAID for a few weeks or months for quick retrieval could be used. And long term, you could have the linear DLT, which is a digital linear tape that creates a jukebox, and that's where disc or tape are retrieved by a robotic arm. But more likely long term is going to be virtual, and that's the most common type of storage. Off-site would be where digital storage is used to ensure data integrity if a catastrophic event were to occur that could destroy data at an institution. SAN is Storage Area Network, and it's dedicated image storage network. So we can see we got the DLT, the jukebox, the RAID, and then another RAID, Workflow Manager and Workflow Workgroup servers. And the purpose is to connect image storage devices in packs. Now the image display is where we have the LCD, liquid crystal display. Liquid crystal is a material state between that of a liquid and a solid. And in the picture on the left-hand side, we're looking at the liquid crystals are randomly oriented on the left, and then they're structured under the influence of an external electric field on the right. So the liquid crystals can be aligned to the action of an external electric field. And it's showing that the same thing happens in the picture on the right-hand side where we have them all facing to the right, and they all then turn up straight up. An LED is a light emitting diode, and the symbol for that is almost identical to a diode, except for it just has a couple arrows showing light coming off. And so the application is general lighting, automobile headlights, traffic signals, and instrument panels. Electroluminescence is where LED emits light when electrically stimulated. The LED does not replace the LCD digital display monitor. What it does, it actually replaces the fluorescent lamp used in earlier LCDs and former monitors. It provides a backlight for a monitor. All video monitors today are LCDs with an LED backlight, which is an intense backlight. The advantages to using an LED as the backlight is that digital display devices are thinner. Digital display devices have a larger active area for visual screen. They can be curved and they're larger video screens. They have a longer life by at least a factor of 2 over the fluorescent backlit display devices. A lower power consumption, reduced electric bill for the hospital, and produce less heat, so improving reading room comfort. The cosine law is where luminance intensity decreases in proportion to the inverse square from the source. So this is talking about the luminance intensity of a digital display device, which is talking about the inverse square law. So when we view the monitor straight on, the luminance intensity is at maximum. If you view it from an angle, the contrast and luminance intensity are reduced. And here's a picture showing that is that the best viewing of a digital display device is straight on, which is on the left-hand side, and on the right-hand side, we're losing brightness and contrast. Ambient light. LCDs are designed to better reduce the influence of ambient light on image contrast. So reduce ambient lighting to near darkness for best viewing. CPOE stands for Computerized Provider Order Entry, and this is where the provider electronically orders all medication, lab, and imaging exams. This streamlines the order process. It improves efficiency and reduces errors and delays in patient care. The CDSS is a clinical decision to support system which analyzes patient medical history, lab results, and current medications. It also offers reminders for preventative care, gives information about drug interactions, and alerts to possible redundant testing. It can flag patients who were improperly diagnosed or missed or given the wrong dose of medication too. Finally, security. Always observe employer-mandated personal computer or network terminal workstation precautions and etiquette, which means to adhere to password protection and log out requirements. So the idea is that you should always log out before you walk away from a computer and then log in when you get there, and never give away your codes, your passwords. Healthcare personnel should never carry or keep patient-specific or patient traceable information on portable media, such as laptops, CDs, flash drives, or hard drives, unless explicitly authorized to do so for a specific purpose. And this concludes our video lesson on digital imaging part 3.